Hey everyone, Dan Hillman here, and I'd like to do a video on electrostatic simulations. You may recall previously I've done a couple other videos on some of Michael Faraday's experiments on electrostatics and also on Gauss's law. And today I'd like to illustrate some of those concepts a little bit more by going over some electrostatic simulations. So previously on my channel, we have talked about Faraday's 1837 experiment on electrostatics. So you recall that in this experiment, there were two concentric spheres, one inner sphere and then an outer sphere, and in between the spheres was this dielectric, and the small sphere was given a positive charge, a known positive charge. The two outer hemispheres were clamped together around the smallest sphere without touching the inner sphere, and you have this dielectric material in between them. The outer sphere was momentarily discharged by connecting it to ground, and then the larger hemispheres were carefully separated with insulating material so that the charge induced on that sphere would not be messed up. And it was measured. It was found to be equal to the charge on the inner sphere, but opposite in sign. And from this, Faraday concluded that there was some kind of displacement flux, which we just call electric flux now, between the inner sphere and the outer sphere, that induced on the outer sphere this charge that was equal to and opposite in sign as the charge on the inner sphere. In Faraday's 1843 ice pail experiment, there was a similar concept. You have this positively charged sphere that was lowered into this metallic ice pail without touching it. And as that happened, then the electric flux from established by the charge in this sphere would induce a charge on the ice pail, and the resulting charge on the ice pail could be measured at the electroscope. Over here you have these gold leaves, and if they're similarly charged, or if they're charged by like charges, then they would repel and there would be a deflection here. So these experiments confirmed that the phenomena of electrostatic induction. Charged particles, charged objects cause an electric field to arise. That electric field has an influence on other metallic objects, and Faraday confirmed this by experiment. So we're going to get into the results of a little simulation that I performed in just a minute here. So I found this tool at this website, PhET, which is University of Colorado's simulation tool. This is a physics, education, and technology simulation tool. It was pretty neat. I'm going to go through that. Some good, nice features of this tool is that it's easy to simulate positive and negative electrical charge. It computes and displays the electric field intensity as a result of these charges at any desired location, and it computes and displays the equipotential contours at any desired location as well. The challenges I have experienced with this tool is that I haven't yet figured out. I don't know if it's possible to model a metallic conductor, which would be an equipotential surface. When you have a metallic conductor, then you have certain boundary conditions, and that makes a difference on things. And I haven't been able to model a metallic conductor in the simulations that I performed. The other thing is that we don't get into any like electrodynamics with this tool. It is just an electrostatics tool. If you bring a charged particle in the presence of an electric field and then let it go, you're not going to see the charges accelerate. But it's a pretty good tool. I kind of enjoyed playing with it, and I want to show it to you, see what I came up with here. So what I wanted to do in this was I wanted to simulate Faraday's electrostatic experiment of concentric spheres. So in the initial scene, in Faraday's experiment, we have an inner sphere that is charged with some charge. In this case, I made the charge 10 nanocoulombs, positively charged. And then we have this outer sphere that is neutrally charged. So you have protons and you have electrons, and they are canceling each other out. So the net charge on the outer sphere is 0 coulombs. So the total charge here from the inner sphere is establishing electric fields all around it. And these green circles here represent equipotential contours. So here it's 232.6 volts. Out here, it's like 172.6 volts. As you get further and further away, then the equipotential contours represent voltages that are getting less and less, and way out in infinity, you have 0 volts. Remember, a volt is the electric potential energy per unit charge. So think of for gravity, you have gravitational potential energy, and you could think of like a gravitational field. You can think of like gravitational potential energy per unit mass. And when you have an object that's lifted up above the ground, then as it gets higher and higher above the ground, it has more and more gravitational potential energy. Well, you could think of, if you divide by that mass, then you have like gravitational potential energy per unit mass. You could think of like these equipotential contours that are parallel with the ground. As you get higher and higher, the gravitational potential energy per unit mass would go up. Well, a voltage is simply the gravitational the electro potential energy, or the electric potential energy per unit charge. That's what a volt is. A volt is a volt per, sorry, 1 second. It's going to come to me. A volt is a joule per coulomb. Joule is a unit of energy. Coulomb is units of electric charge. A volt is a joule per coulomb. Okay, so scene 2, this is after that, an initial transient response. What happens is this positively charged sphere is attracting the negative charges on the outer sphere and kind of repelling the positive charges on the outer sphere. Now, the positive charges are in the nuclei of the atoms, and they're kind of bound in the crystalline structure. So they're kind of just going to stay where they are. But the negative charges are going to kind of come right to the surface, the inner surface of this outer conductor. And they're going to stay right there on the surface. They're not going to be able to escape the crystal lattice of the inner sphere. It's not like we're hitting it with high energy photons, and you have the whole work function, and you get into some Einsteinian stuff there. But we're not talking about that right now. So these negative charges will be brought toward the edge of the outer sphere, the inner edge of the outer sphere, in such a way that the net charge on the inner sphere, on the inner edge of the outer sphere, would cancel, or would be the same but oppositely charged as the charge here. So if we have 10 nanocoulombs on the inner sphere, you would have about negative 10 nanocoulombs on the inner edge of the outer sphere. But you also have all these extra positive charges on the outer sphere. So the net charge on this outer sphere is still 0. But you can just see like there's this, the negative charges have kind of come close to the surface. The free negative charges have come close to the inner surface, and the positive charges kind of stayed where they are because they're just kind of stuck where they are in the nuclei of their respective atoms. But now, if you recall, in this experiment, Faraday touched the outer sphere with a ground, or touched the outer sphere to a ground. So a ground is basically just this reservoir of a whole bunch of free electrons that are just negatively charged electrons here. And so as the ground gets close to the sphere, you can see these field lines. There's basically a dipole of sorts here. We have a positively charged these net positively charged spheres here, and this is like negatively charged. And so you have all these electric fields that are coming from the positively charged place to the negatively charged place. Okay, and you can see like over here, these negative charges are very attracted to these positive charges, and these positive charges are very attracted to these negative charges. And when they finally touch, then electrons flow freely from the ground onto the sphere. What it ends up doing is it neutralizes the outer part of the outer sphere here. And so what you end up with is now the outer edge of the outer sphere is now neutrally charged, but the inner edge of the outer sphere is negatively charged. So the net charge now on the outer sphere is negative, and it's negative, in this case, negative 10 coulombs. You have 10 coulombs on this inner sphere, so the net charge on this outer sphere is negative 10 coulombs. And as a result of this, the voltage out here is very, very low. You can see the fields out here. You see the dark, this red basically represents a high voltage. The blue represents like a negative voltage. But out here in the black, this pretty much is close to 0 voltage. And so you can see here, like this is like 0.66 volts per meter for the field. See how small these field values are. Not much going on here in terms of the voltage. The equipotential contours are very low. So yeah, so that's how that plays out. And that's kind of all I have for that. And now what I'd like to do is I'd like to show you the tool itself and just play around with that for a little bit and kind of let you see what that's like. So just give me a second here. I'm going to exit this. I'm going to stop sharing this. I'm going to share my screen again. And I'm going to find the website. I have too many windows open. Bear with me. Okay, so here's the tool. Again, just give me 1 second. So I'm just going to drag, here's 1 nanocoulomb of charge, and you can see I drag it over here, and you can see all these electric fields, the orientations of the electric fields anyway, and you kind of see the brightness where the electric fields are very high, and as it fades out, the electric fields are falling off. But we can do all kinds of things here. We can look at voltage. Let's throw some more charges in there. Okay, so these charges are establishing electric fields all over the place, and this is a very good visualization tool. Now, I'm going to take this. This is like an equipotential meter of sorts, and I'll go right here, for example. And here we have an equipotential contour. And I'll do another one over here. And I'll do another one over here. And I'll do one over here. Okay, I'll bring this back over here. And now we can look at some of the values here. So at this equipotential contour, this is 70.4 volts. In other words, 70.4 joules per coulomb all along this equipotential contour. In other words, if you brought a charge to this contour, then its electric potential energy per unit charge would be 70.4 joules per coulomb. Out here, it would be 29 joules per coulomb. Out here, it would be 14.7 joules per coulomb. Again, a volt is a joule per coulomb. and out here it'd be 11.3 joules per coulomb, and out, you know, in infinity it'd be 0 joules per coulomb. Okay, so I'll throw another charge in here, and so then those equipotential contours went away because I put another charge. I changed everything. How about some negative charges? So if I do like a negative charge over here, now we have a dipole going on. If I let's put a few more here, and you can see now, so we have these positive charges here and these negative charges here. And so negative charges establish an electric field oriented toward it, and positive charges establish an electric field oriented away from it. And so all over here, we see the electric fields that are the superposition of all these charges. In fact, it's something I didn't show you last time, but I'll bring this sensor over here. This is an electric field sensor. So over here you can see the electric field over here is like 5.24 volts per meter oriented in this direction. And I can move it. And as we move it, you see how the electric field changes. And as you get closer and closer to these positive charges, look how intense this electric field is. As you get further and further away, it gets smaller and smaller and smaller. You can see the orientation. As you get close here, now you can see how intense it is, oriented toward the negative charges. You go around here, like right here, the electric field is very high. Right here, it's like 456 volts per meter, oriented away from the positive charges and toward the negative charges. This is a pretty neat tool. And all this is basically just Coulomb's law, just being applied. Pretty straightforward. Just superposition of vectors and the application of Coulomb's law. Pretty neat. Again, we could do equipotential and you could do a bunch of these. So if you want, you could do something like this. You can kind of get a sense of what the electric fields are like all over the place. You can have all kinds of fun with this, and if you're not careful, you can spend too much time on this. But it does give you a good idea of what's actually going on visually. When you think of charges, you should have in your mind, you should picture in your mind electric fields all over the place. And you should also picture in your mind equipotential contours all over the place. So now with two charges here, a dipole, positive and negative charges, here's an equipotential surface. And here's another one. And here's another one. Here's another one. Here's another one. We'll do another one right here. And maybe one more over here. And I think that's good. That's enough. We're getting a little busy here. Of course, you could, when you're getting busy, you can just kind of take these and bring them back over here. And that way it's less busy. You could turn this off if you want. So notice if you bring like these field meters to the equipotential contours, the orientation of the fields are always perpendicular to the contours. And that's because the gradient of the voltage, or the gradient of the equipotential contours, the gradient of the voltage is the electric field. So the electric field is always going to be directed in the direction that's perpendicular to the equipotential contours. And as the equipotential contours get closer and closer and closer to each other, then the electric field, which is in volts per meter, goes up dramatically. Whereas when the equipotential so over here, like we're at what, 458 volts per meter. But here I'm pretty much staying on the equipotential contour, but up here you can see it's like 18.3 volts per meter. You can see how far apart these equipotential contours are over here as compared to over here. So lots of stuff here that gives you insight into what's actually going on with the physics. I really enjoyed using this tool, and I think it's going to be very helpful to give people an idea of what is actually going on with the physics of electrostatics. That's all we've got for now. I hope you enjoyed this, and I'll see you next time.